Hey everyone, welcome back to discussion 6. This time we were talking about circular motion, and so let's just hop right into it. So we are told that we need to look at textbook page 117, problems 62 and 63. So let's get to page 117. Okay, problem 62. A ball starts from rest at the left end of the track shown in the figure. The ball flies off the right end of the track and follows the parabolic trajectory shown. At each instant, 1 and 2, the direction of the acceleration is the direction of the acceleration of the ball, upwards, downwards, to the right, to the left, or is the acceleration 0? All right, so we have two scenarios, and it's asking us to talk about the concept of the acceleration. All right. Well, let's open up a file here, and let's draw a picture that's a little bit more clear so that we can see. Well, hopefully it's more clear. I'll do my best here. So we go down. This comes up, right? It's a track. This extends on for a long time. This is where the ball is launched. This is scenario 2 over here. This is scenario 1. So we have a ball. This is just to indicate that it's rolling down the hill. And I would say that this is in scenario 1 here. Right, okay. So it's asking, we are being asked, what is the direction of the acceleration? Okay, so here, if we look at this position 1, we are following some circular path, right? It's almost as though we are tethered to something. So this is essentially just circular motion, and the acceleration is going to be pointed upwards due to centripetal acceleration. So this one is going to be upwards. That's my answer. Okay, so the next one, we have this ball is traveling in this direction. This also is following a parabolic arc. Notice that we're not tethered to any track or anything, but we're still making this sort of motion, and we already know what direction the acceleration of gravity goes in, right? It's negative y hat direction, which is going to be downwards. So we have opposite accelerations happening. So in acceleration 1, we have the direction is upwards, and in number 2, it's downwards. Those are my answers. And then let's move on to the next part of the problem. A ball starts from rest at the left end of the track. Same scenario. It flies off the right end of the track and follows the trajectory. Suppose the right end of the track is 1 meter above the floor. 1 meter above the floor and makes an angle of 30 degrees with the horizontal. Okay, also suppose the ball leaves the track with a speed of 4 meters per second, and determine where the ball hits the floor. Okay, so we are given some information that we can actually use here. We are told that this is going to be, 30 degrees with the horizontal, right? So this is 30 degrees. We're also told that the initial speed, v0, is going to equal 4 meters per second. We are told that this distance is 1 meter. Okay, We know what acceleration is once it leaves the track. Let's see, what else? It wants us to determine what is the value of x over here when it hits the floor. Probably it's over here more. X. This is going to be your range. Well, let's just call it x. Where is this? Okay. All right, so let's see. Let's set this up. So we have our kinematic equations. We have a two-dimensional thing happening here. Y naught plus V naught t plus half a t squared, right? And in this V naught situation here, it's actually V naught y. We can solve for this. Okay, so y naught is 1 meter. So, and final y is 0. We've done this before. We did this in the last lecture. So 1 plus V naught is 4 meters per second times sine, since we're only doing the y direction right now, we're going to be sine 30 degrees plus, minus 1/2 9.81 times time squared. I forgot to put time squared. That's a common mistake. Okay, so now what are we trying to solve for? We need to determine when the ball hits the floor, or where the ball hits the floor. And in order to do that, we need to know the time, the total elapsed time. So that's what I'm trying to solve for up here. So we need this information in order to plug it into the x equation. Okay, so t, let's see, let's just double check. Just as before, as we've done a couple times before, we pretty much just solve a quadratic equation for t, and then we plug in our values. So I'm just going to write down the simplified version. This is squared, and over here. Okay, so now we pretty much just plug in the values for this. Okay, so then what I do is I plug in, what was it? It was V naught y. It's going to be 4, what was it, sine 30? Sine 30 is actually 1/2, so that's actually 2 over 9. This is negative 9.81 plus or minus. What was this again? 2. So this is actually going to be 4 over 9.81 squared plus 2 over 9.81. Right. This should be approximately 0.7. Let's see if I get that. So plugging this in, I get 0.66921. No, excuse me, 0.699291, or approximately 0.7 seconds. So the total elapsed time for this thing to fall off of the track is a little under a second. That's pretty quick, and that actually makes sense because we're actually starting pretty low. We're only a meter off the ground. The ball is traveling rather slowly. It's 4 meters per second. So this makes sense to me. Okay, so now then we just have to plug this into our equation. X is equal to x naught plus, what do I have over here? V naught x, V naught sub x times t. We're going to call x naught 0 because we want to know how far away from this thing has this ball traveled. So this is going to be 0 here. Okay, so this gives us 4 cosine 30 times 0.7. This is going to be square. Okay, so we got 2 times square root of 3 times 0.7. This is going to be 2.422 meters. 2.4 meters away. So that's where the ball hits the floor. Okay? Okay, let's check out problem number 42. A pendulum constructed with a bowling ball at the end of a cable, 4 meters in length, has an acceleration vector when it is 24.7 degrees past the lowest point in its swing. So let's start setting this problem up. Let's draw a picture. So number 42, we have a ceiling, we have a pendulum, this is theta. Theta is equal to 24.7. Our acceleration vector is negative 8.5 I hat plus 24.3 j hat. Okay, so part A says, well, let's also, before we move on, let's draw our axes here. This is going to be x hat, right? So part A asks, sketch the scalar components of the acceleration vector in a vector diagram at this point in the pendulum's motion. Okay, well, let's just do it over here. So we're told that it's going negative 8.5 in the I hat direction. So I hat is in the x direction. It's a negative, right? This is a negative value, so it's going this way. And then we have a positive value here, 24.3. It's about 3 times the size of that, so it goes straight up. About like that, I'd say. Maybe that's a little extreme. Like this. Let's do it like this. Something like that, I'd say. Negative x hat direction, positive y hat direction. Okay, anyway, next part. What is the magnitude of the radial acceleration of the pendulum at this point? Okay, so we can find this by sketching a force diagram. So here's our pendulum bob. Here's our pendulum bob. Here's the tension force that is connected to the ceiling, right? That's going to equal also our centripetal acceleration. Okay, and we also have, what else do we have? We also have a weight force. So those are really the only two things that are influencing our pendulum. We have a tension from the rope, and we have a weight force, right? So tension and then the rope, and then we have some acceleration vector that we're given. Let's draw it, some acceleration vector over here. That's what we're given. So this is what we have going on. So let's write this out. We have mass of the bob times our acceleration. And then this is going to be mass times the, we'll call this the centripetal acceleration, plus mass times the gravitational acceleration. Okay, so now we divide out the mass. Okay, now we're just left with some accelerations. We have centripetal plus gravitational. So in the y hat direction, we have ACY plus minus G. Okay? In the x hat direction, we have ACX hat, and that's all we have, because we just have, this is our final vector. So we just have gravitation, and then we have the tension force, okay? So the y component of the tension force is going to cancel this out, and the x component of the tension force is also going to cancel this. Is going to cancel this out. So from the math, you can see it a little clearer. Here's our y direction. We have the tension centripetal acceleration force, and we also have the gravitational force. Here in the x hat direction, we only have the centripetal force in the x hat direction. Okay, so what we have, AX is equal to, let's call this way, and then if we look at our diagram, we actually have, here's theta, and so this component here is actually going to be sine theta, right? So x hat in this direction is sine theta. which is equal to 24.7 degrees. We're also told that the acceleration vector in the x-hat direction, we have an overall acceleration vector, is negative 8.5. So let's do this. So now we can solve. For AC is equal to negative 8.5 over sine 24.7. All right. Okay, so plugging that into the calculator, we get a value of negative 20.344. Oops, I didn't write it down. 3446, right? So that's all approximately negative 20 point, what do we have? 535, we'd say. Or you could say 20.4, but this is fine. And so remember that we're looking for the magnitude of the radial, they call it the radial acceleration in the book. It's centripetal acceleration. So this means that we have 20.35 meters per second squared. Okay, so that's the magnitude of the radial acceleration at this point. Okay, so now, using this information, we can also find the velocity and the speed. So recall from, if you look in the summary in your book, you'll have this relationship, v squared over r. Okay? Now we know what this value is, r, and we know what this value is. So we have only one unknown in our equation. So let's do this. R times AC square root is equal to v. Okay, so v is equal to 4 times 20.35. Plugging these values into my calculator, I end up with a value of 9.02 meters per second. Okay, and if we check the units, well, we know the units are going to work out on this because we have this here is meters squared per second squared over meters. That's meters per second squared. Yeah, so this is going to be, excuse me, this here, this is meters per second squared. So this is meters squared per second squared under a square root. That gives us meters per second. We're good. Okay, so that's the speed. Now, if we want the velocity, we take Vx is going to be the magnitude, right? That's what this is. This is our speed. V times sine 24.7, because recall that this is actually, since theta is up here, our sine theta is in the x direction, and our cosine theta is in the y hat direction, okay? So that puts us here. Let's just write this out. 9.02 times that, and then v sub y is going to be 9.02 times cosine 24.7, and let's plug these in. Okay, so plugging those into my calculator on Wolfram, really, I'm just using Wolfram Alpha, I end up with these values here. In the x direction, we have 3.769 meters per second, and then we have 8.195 meters per second in the y hat direction. That actually gives us a velocity of, well, if we're just rounding up, let's just call it 3.8, right? We'll just say it's approximately, you can do your own rounding, but this would be I hat plus, and then we'll call this 8.2 J hat, and this is all meters per second. And this actually makes sense, because if we check this, so we're actually moving in the positive x direction and the positive y direction. And the way we set up the problem, oh, that's weird. The way we've set up the problem, the pendulum is actually moving in this direction. Okay, the acceleration is pointing in the other direction, but the velocity is going this way and this way. Okay. All right, so that's the solution for that problem. Moving on, we have D3. It's going to be page 118, problems 80 and 81. Let's go see what those are. Cosmic rays are high-speed charged particles from space. They are harmful to people, other organisms, and equipment. Fortunately, the Earth's upper atmosphere and magnetic field act to shield us from these particles. The trajectory of charged particles trapped by the Earth's atmosphere is complicated. Certainly. In this problem, we will explore a simpler scenario in which a single charged particle is trapped by a magnetic field and travels in a helical path. The position of this particle is given by this vector. A, B, and omega are constants. So we have 4 parts to this problem, it looks like. Part A, substitute values for t to confirm graphically that the path of the particle is a helix. Okay. So let's write down our function that we're given. This is I hat plus A sine omega t j hat plus B t k hat. Okay. Now it wants us to plot. Okay, the simplest way to go through this is we can just sort of observe that for our position vector r, let's simplify it. Let's say that A is 1. Let's say that omega is 1. Let's say that B is also 1. So we're just looking to plot this thing. It doesn't have to be super complicated. So what we're going to find is that, let's say we have cosine x plus sine x plus x. Okay, let's say that this is our new position function. We'll call this r prime. Okay, so what's going to happen is that cosine x plus sine x is going to be a circle, right? So if we plot sine x here and then we have cosine x here, what happens is that we actually end up getting, so let's say that this is y and this is x, we're actually going to end up getting a continuous circle for all values of x. That's what's going to happen in a 2-dimensional plane. In a 3-dimensional plane, so now we have, let's go here, we have, this is a 3rd dimension. This is y hat, this is x hat. This will be z hat. So now let's think about, here's our xy plane. Remember I just said that we would have a circle. It's going to look like an oval because it's supposed to be flat, right? But now as x increases, so does the height, so does the z value, because this is in z hat direction, right? So as x increases, this is also going to increase upwards, like this. Oops. So what's going to happen is, as this thing moves in a circle, it's going to increase in height. That was really strange. So as this thing, I'll just say it again, as this thing moves in a circle, it's going to increase in height, forming a helix. Let's imagine that these circles are all even. Okay? So this is what the graph would look like. And in fact, we're told that as well. You can also plot this in Wolfram or Desmos or Symbolab. Those are 3 powerful graphing apps that I use on my phone and on my computer. And you should get something very similar. Okay, so that's your graph. Okay, part B. Find velocity and acceleration. Okay, no problem. Here's our position function. Let's recall that dr dt is equal to velocity. Also, dv dt is equal to acceleration. So we need to do this derivative twice. Okay, so v is equal to, v of t is equal to a times omega, negative a omega sine omega t I hat, plus a omega cosine omega t j hat, plus b k hat. Acceleration with respect to time is equal to negative a omega squared cosine omega t I hat I hat minus a omega squared sine omega t j hat plus, oh, that's 0. So there is nothing in the z direction. No acceleration in the z direction. So that tells us that we have a constant change in velocity in the x direction and y direction. And that makes sense because we're moving in a circle. So that's going to be consistent. And this also tells us that this is a constant. There is no dependence on t here. This is just a constant motion straight up. Just like we were saying here, this is straight up. There's no change in the velocity moving upwards. Okay? And that's what we have. There's zero k hat direction in the acceleration. Okay, so that's part B. Part C is describe the z component of v of t and a of t. Oh, I just did that actually. I just was describing the z component. But I'll say it again. I will say it again because this is part of it. So, in v, since this is specifically asked in the question, we have constant motion in the z hat direction. Constant motion in, we'll call it k hat direction, right? The value is b k hat. That's what we have. It's just going to keep going up and up and up. And for acceleration, we have 0. We have no acceleration in k hat. Okay? So, part D. Do R, V, and A in this problem apply only to charged particles in a magnetic field? Or do they apply to any particle moving in a helical path? Explain. Well, this is not explicitly dependent on a magnetic field. There is no function, like there's no function with respect to a B field in this. It's dependent on time. So it can apply to any particle. This can apply to any particle moving in a helical path. So yeah, I mean, as long as the medium is consistent, it should be fine. I'm going to say this applies to any particle in a helical path. Not just a B field. Okay? All right. B field, by the way, I don't know if this has come up yet. Probably not. B field is a magnetic field. Okay, what is next? 80 and 81. All right, more of this. Let's see. An experimentalist in a laboratory finds that a particle has a helical path, just like before. The position of this particle in the laboratory frame is given by a very similar function. Very similar function. The difference would be our constant of motion is v sub z. R, v, z, and omega are constants. A moving frame has velocity v sub z k hat relative to the laboratory frame. So this is a rather challenging problem. I think that we should write down what we know and what is given to us in the abstract as well. So r is equal to big R cosine omega t x hat plus big R sine omega t y hat v sub z times t, and that's in the z hat direction. So there I go again. I'm changing my z hats from k hat. But I like to use this notation, so it can be tricky for me to remember. But let's be consistent with the problem that's given to us in the book. Okay. All right, we're also given that there's a moving frame in the laboratory from the laboratory frame, we see this as moving with this velocity. So notice that here's our particle. It's moving in a circle plus moving up as well, so this is going to be a helix as we described, but this is a constant motion, and this is also a constant motion. So what is the path of the particle in the moving frame? So for part A, and it clearly explains in the book by, it's marked C, that means conceptual, right? So that means that there shouldn't be too much calculation here. This is just kind of describing what's going on, right? So what is the path of the particle in the moving frame? Well, look here. Again, this thing is moving in a circle, just like we described before, and it's also moving up as in a helix, right? So we have this kind of motion going on in the lab. This frame is also moving up with the same velocity, right? So if we integrated this, let's call it the moving frame lab, this would actually be vz times t, right? So it's exactly the same. So the motion in the z direction is the same for the moving frame as it is for the particle. So the person in this frame is only, if there is a person in this frame looking at the particle, they're only going to see the particle moving in the x and y plane. So to draw it out, let's make it a little more, try to make it more explicit if we can. This is the best helix I can do right now. This thing is moving up. Constant velocity in the z direction. Right? So, and then we have a moving frame. I need to draw a moving frame. Here's a frame, and we have an observer in the frame looking at the particle. This frame is also moving with this velocity in the same direction at the same speed at the same time, right? So now all this person is seeing over here, all this person is seeing is this thing is just moving in circles because they're both going up at the same time, right? So that's kind of fun. Anyway, if so here is the moving frame position path. Right, this is the position of the moving frame. So what the moving frame is going to see, I'm going to say here is going to be, it's going to see this same thing, but no acceleration in the k hat, no velocity in the k hat direction either. There we go again. I hat, j hat. Okay, this is viewed from the frame. Next part, we're asked what is the velocity of the particle as a function of time relative to the moving frame. If I can get this to work, we have this position vector here, right? So as the moving frame is going up at the same time as the particle, this is what the observer is seeing as the position of the particle. So it wants to know what is the velocity. We just have to take a derivative. R omega sine omega t I hat, excuse me, plus r omega cosine omega t j hat. That's the velocity of the particle as a function of time relative to the moving frame. Or I would say from the moving frame. From the moving frame. That's what I would describe that as. Sometimes the language can get a little confusing in physics textbooks, to be honest. Okay. We're almost done with this problem, so we'll probably get out a few minutes early. What is the acceleration of the particle in each frame? Well, we've already found this part, so let's just keep going with this one. This is equal to negative r omega squared cosine omega t I hat minus r omega squared sine omega t j hat. And this is, again, from the moving frame. This is as viewed. I should say as viewed Okay, so now where was our original position? We'll take this guy here. So this is the velocity and acceleration of the particle as viewed from the moving frame. Now we have, here's our position. So just take a couple derivatives real quick. So v is equal to negative r omega sine omega t I hat r omega cosine omega t j hat plus v sub z k hat. Okay, so this is as viewed from the lab frame, as viewed from the lab frame. All right, now we have A is equal to negative r omega squared cosine omega t I hat minus r omega squared sine omega t j hat plus 0, because this is a constant. Okay, so that's nothing. So let's just take this, let's copy, bring these down here so we can get a better look at them. I can't see them, they're way over there, I can't see them anymore. Okay, here. So we have two acceleration functions. One as viewed from the lab here, and one as viewed from the moving frame that's moving in line with the particle. We are asked, what is the acceleration of the particle in each frame? So we found that, and then part D, it says, how should the acceleration in each frame be related? Does your answer to part C make sense? And explain it. Okay, well, the only acceleration in either frame is with respect to the circular path in the xy plane. So what I mean by that is the only real change in the acceleration, the change in the velocity, is going to be along this plane. And that's just because it's moving in circles. I wouldn't say the angular speed is changing. We're not given any indication that that's true. So it's just moving in circles, and that's the acceleration. And really that makes sense. I mean, it's moving with a constant motion as viewed from the lab frame. It's moving constantly in the upwards direction, and it's just spinning in a circle constantly, right? And from the frame that's moving upwards, that's viewing it, it's not moving upwards as viewed from the frame that is moving upwards. So if you're standing in the moving frame, is what I'm saying. If you're standing in the moving frame, it's not moving upwards. It's moving with you. It just looks like it's stationary, right? And it's just still moving in a circle. And so yeah, I mean, it should be related. I mean, nothing is really, there's no outside forces really acting on this, other than the one that's making it move upwards as viewed from the lab frame. It makes sense. So to answer the question, it makes sense. Yep. Okay, so that's going to be it for today. I encourage you to look at this problem a little closer and think about it more. And we'll see you next time.